Welcome to Understand Chemistry. This is Dr. Bilal. In this video, I will talk about a widely used polymerization process, the solution polymerization. In this method, monomers are polymerized in a solvent which can create either a homogeneous system where both monomer and polymer are soluble, or a heterogeneous one where the polymer precipitates out. The solvent plays a crucial role. It helps control viscosity, which is important for maintaining reaction kinetics, and it also aids in dissipating heat generated during polymerization. However, the choice of solvent is critical. It must not interfere with the reaction or reduce the molecular weight of the resulting polymer. Let us take a closer look at homogeneous polymerization. In this method, the monomer and initiators and resulting polymer are all soluble in solvent, creating a uniform reaction medium. This homogeneity allows for consistent reaction kinetics, making it easier to control the polymerization process. One major advantage is that the solvent reduces viscosity, which helps to reduce the gel effect that we often see in bulk polymerization. By keeping the mixture fluid, the solvent improves heat dissipation and molecular mobility, allowing for smoother propagation and better control over termination. A key reaction in this setup is chain transfer to solvent, which plays a crucial role in controlling the molar mass of the polymer. By adjusting the solvent type and concentration, we can fine-tune the molar mass distribution. Typically, homogeneous polymerization yields polymer with a dispersity in the range of 1.5 to 3, indicating a moderately broad molecular weight distribution. Let us walk through a practical example of solution polymerization using vinyl acetate in benzene. In this setup, vinyl acetate acts as monomer, benzene is the solvent, and AIBN is used as the radical initiator. All three components are soluble, making this a classical case of homogeneous polymerization. As the reaction proceeds, the vinyl acetate undergoes radical polymerization to form polyvinyl acetate. The viscosity of the solution gradually increases as polymer chains grow, so a dilute solution is used to avoid the gel effect, which can cause uncontrolled autoacceleration. Once the reaction is complete, the polymer is recovered by precipitating it into a poor solvent like ethanol. Polyvinyl acetate has important applications in adhesives and coating, but it can also be chemically transformed. Through hydrolysis, typically using water and sodium hydroxide, polyvinyl acetate is converted to polyvinyl alcohol, which is a water-soluble polymer. This reaction also produces acetic acid as a byproduct. Polyvinyl alcohol is widely used in films, textile, and emulsifiers. Once we have polyvinyl alcohol, we can react it with butyryl aldehyde to form polyvinyl butyryl. This reaction is essential in producing the inner lining of safety glass. Let us talk about heterogeneous polymerization. This is also called precipitation polymerization. Here, the monomer and initiator dissolve completely in the solvent. However, the polymer chain as it grows is insoluble. It precipitates out, forming solid particles. Inside each particle, we see the gel effect, where termination is suspended. For this type of reaction, we must also consider chain transfer to solvent. These reactions result in broad molar mass distribution with dispersity typically between 3 and 10. Let us look at the polymerization of acrylonitrile in methanol, which is a classical example of precipitation polymerization. Acrylonitrile is carcinogenic, so it must be handled with extreme care. The initiator used here is AIBN, typically at 0.5 to 1% by weight of the monomer. Methanol acts as poor solvent for the resulting polymer, causing polyacrylonitrile to precipitate out as the reaction proceeds. This polymer is widely used in textile under the name acrylon, but Polyacrylonitrile's story does not end here. When polyacrylonitrile is heated in presence of oxygen, it undergoes series of cyclization and oxidation reactions, forming ladder polymers. These are rigid, conjugated structure with exceptional thermal stability. These black ladder polymers are key precursors in the production of carbon fibers used in aerospace and high performance materials. So from a simple monomer, we get a pathway to advanced heat resistant polymers with real world impact. Hope you understand the concept of solution polymerization. Thanks for watching.